Okay, hello everyone. Welcome to this broadcast, this meetup today, hosted by Machine Learning in Healthcare. My name is Vince Madai. I'm the main organizer of Machine Learning in Healthcare and also of the Berlin chapter. With me is another organizer today.
Hello, I'm Sophia, and I'm of the Berlin chapter of the Machine Learning of Healthcare meetup. And thank you for joining us today. First of all, some announcements. We have a Slido where you can join us and enter this link that we will about to be sharing, and then you can post your questions there, and we will get to them towards the beginning of the session. And another exciting thing is that we're raffling 3 PyCharm licenses in a few days. So if you want to win, then please follow us on one of our on our LinkedIn channel or our meetup groups or on Twitter, and in a few days we will raffle out the winners. And thank you for joining us.
Yes, and it is a very, very big pleasure to have Lars Maaløe with us today. And Lars Maaløe is co-founder and CTO of Corti, a voice-based digital assistant powered by AI, capable of understanding patients talking in natural language. In the past, Lars has worked with various tech companies such as Apple, and he holds a PhD in machine learning from the Technical University in Denmark. And we are very, very much looking forward to his talk about quantifying uncertainty on human medical conversations by deep learning. Welcome, Lars.
Thank you so much. And thank you so much for the invitation and letting me present to all of you that I can't see. And I basically can't see how many there are, but hopefully there are someone out there that has logged in and are eager to hear my presentation today. Hopefully also you are more than welcome in posting questions when I go through the presentation. And if you have something that you would like to know more about, then post a question and I can jump to that question and hopefully answer that question in order to make it a little bit more dynamic than me just feeling that I'm sitting alone by myself doing a presentation. So as introduced, I'm Lars Maaløe. I'm one of the co-founders of Corti, and we started Corti back in 2016. We are approximately 55 people now, and we have a lot of machine learning specialists hired and data scientists, software engineers in order to make our software working. I'm going to give you a brief introduction, hopefully brief introduction to our company and what we do, and give you some demos, and then I'm gonna prove you some validation points of our technology within the healthcare space, which is of course very important since this is healthcare. And then I'm gonna move towards the actual promise of the presentation, which is the quantifying uncertainty part. Which just to clarify from the beginning of this, and this is a spoiler alert, is that we have not solved it as a company, but we are eager in order to solve it, and we are eagerly working on it through various research projects. So I'm gonna shed some light on one of the research projects that we finalized at the end of 2019 and that we're using now, and give you some insights on where we're bringing that currently through PhD programs and research collaborations with various universities around the world. So I'm normally making this presentation just to start from the beginning, and this is for Vince warned me that this is probably a very, very knowledgeable AI crowd. So so this is probably going to bore you, and you're probably going to roll your eyes off this slide saying that AI is starting to look like us. It's also starting to get smarter than us. However, when you look at the various like simple things that an AI should be able to do, it's basically failing. We can go into the specifics of various points on why it's failing, but as far as we can see right now is that it is not as good as advertised, and it's really difficult to make an AI system that actually do the same thing as a human can do by basically automation while thinking about very, very difficult reasoning processes at the same time. So I have this video in mind every time I speak about AI, and also want to underline the fact that I'm not the biggest fan of the connotation of using the terminology of AI, because I don't think this is that the systems that we're creating in a lot of instances are actual intelligence. What I do like is a scientist called Judea Pearl, and his explanation of where modern day deep learning systems and normal machine learning is. And he's saying that potentially you have heard about the ladder of causation from him, but basically what he's saying at the ladder of causation is that the first step in the ladder of causation is the ability to be able to see. And that's where he places the modern day machine learning systems, that they're able to see data and learn associations within data. Then he's saying, like, the next step on the ladder of causation is a baby, a human baby, that is able to start to fumble around in the environment and interact with the environment in order to learn. Thereby, the baby is able to actively say that I don't know that much about this paradigm, and therefore I want to go and interact with that in order to learn more about it. That's potentially why a baby is keeping on drinking the glass of milk to the floor for a couple of times, because the baby is learning the laws of Newton. At one point, though, the baby is probably getting into the point of this actually being amusing. Then the last step of the ladder of causation is the imagination part that human beings are actually able to do. We are able to use our domain knowledge from the current empirical evidence-driven world in order to imagine something else. If this, then that. So basically, the main point with this slide, from my perspective, is that the modern deep learning and AI systems are quite simple. And then some of you would say, what about reinforcement learning? And then I would counter right now with saying that reinforcement learning systems has a long way to go before they can really start interacting with an environment in a similar way as a baby. On top of that, our AI systems are extremely data cumbersome. They need a lot of labeled data in order to actually learn, and it's taking a gruesome amount of time for learning something quite simple. However, when it's learned, it can actually solve quite complex problems, and especially deep learning systems are getting really good at learning to find patterns in really complex input distributions, and thereby extract those patterns for decision processes. For instance, in the autonomous vehicle, as you see all the way to the right in this slide. Here, my point is that a lot of the AI systems that we see today, because they are able to see and they are able to quantify, look at associations within data, we see as a company as well, we see the necessity of AI systems today being the best possible co-driver for us humans. And here we use the word augmentation, as many of you probably know. Not that many people in the outside knows that. However, basically that the AI system is able to assist us as human beings in making better decisions. That's where we believe that these AI systems are really strong, because as soon as they have learned on all of this data, they can also crunch the data quite quickly. They take a long time to learn, but they crunch the data quite quickly. But as soon as they have learned something from this data, they can help us humans and augment our capabilities, similar to what a hearing aid can and glasses. There exist multiple areas where an augmentation system makes sense, from driving a vehicle towards finding a tumor inside an MRI scan, or going into the decision process of a human dialogue. And the third point here is the decision process of a human dialogue. That is where we as a company are really good. We have built an AI system that listen in on medical conversations and help the medical professional in making a better decision. So basically, we have the AI system that crunches all of the audio in close to real time in order to find patterns in that audio It finds patterns whether they correlate with one of the outcomes that it has learned from the registry data, in order to give the medical professional some input on whether this patient should go to the left or to the right. In order to solve this, we started with a subdomain within healthcare, and because like healthcare conversations are vast, and they're extremely varied in terms of what can be talked about during these conversations. So what we knew from the get-go is that we wanted to see if we could build a machine learning system that could tap into some of the most acute conversations, because we knew that when a conversation is the most acute within the healthcare sector, the person that needs to make the decision has very little option of asking someone for an additional advice. Therefore, and the doctor looking at the tumor scan can ask numerous other doctors of whether they believe that this is a tumor. They can make a majority voting, and they can do another one the day after. It's not as acute. But when someone is calling in for a 112 service or a 911 service, then they need the help, and they need it quickly. And therefore, the one making the decision needs to be swift in action and prompt in sending the right response, and also ensuring that they instruct on the right pre-arrival instructions. So that was the most critical medical incident that we could think about. Another thing from a machine learning perspective is that within these conversations, because they're so acute, we also knew that there was no outside data. And what I mean by that is that the dissemination between the patient and the medical professional is confined to the interval of the conversation. Hence, the medical professional is almost never looking at other information than the information that they're retrieving from the patient. That makes this a really good environment to test a machine learning system, because there's only one data source to begin with. This is, of course, a really complex data source, which is audio, and it's clean audio, or it's stressed and noisy audio, but pure audio coming into the system. The third point in starting in immersive medical services is that there is loads of data. Since these immersive medical services, they need to record the data. So every specific emergency call that comes in is stored for quality assurance purposes and also legal purposes. That made it possible to actually learn from these audio calls and see if we could extract some useful features in order to make the medical professional making a better decision for the future. So we, as a company, we have built this machine learning framework in order to listen into the conversation as they come into the medical professional. However, that machine learning also gives us the capability of analyzing the machine learning after, or analyzing the call data after the phone was hung up. Thereby, we can analyze all of the call data, and we can analyze them across incidents. We can find things like questions, symptoms, and we can also find more intricate things like whether this call taker is normally speaking a little bit too fast, as opposed to the other call takers on the emergency medical service, and whether this feature is having a positive or negative impact on the performance. Also, whether the call taker is asking the same questions a lot of times and don't give that much time for the caller to answer. All of those nitty-gritty things in patterns that we can detect in order to highlight them and make the dissemination between the patient in the acute situation and the medical professional as efficient as possible. We do that post in the analysis. And also what we do as a company is that we help on the pre-screening. So what is the pre-screening here? That is before the caller can get to a human being. Our belief as a company is that it's better to talk to an AI system than no one at all. So our AI system can assist in assessing the patient calling in. so that if there is a long call queue to a 911 service in the US, for instance, that is happening, especially in certain areas, then we can start getting some dissemination from the caller before they actually reach a human being, and provide that human being with that dissemination. Next, I'm gonna try to show you a small demo of the system, and a demo is best when you basically show the actual system and how it works in a real life emergency medical service phone call. I've just changed this to my speakers, and hopefully you can hear the audio. If not, I'm sure that Vince will write me a note here on the comments side.
Apartment 202?
Yep.
What's going on there?
My dad's either having a heart attack or a stroke or cardiac arrest. I'm not sure.
What's going on? Is he conscious and awake?
No. I mean, he's breathing, I think, but he's on the floor. And
Okay, I want you to go look at him and see for sure if he's breathing, okay? And I'll stay on the phone with you.
He's breathing. My husband
Okay.
says he's breathing.
Okay. Is labor breathing? Is he responding to you at all?
No.
Okay. Does he have a history of cardiac problems?
No.
Okay. I got some help coming. Hang on the phone with me here. So if before the firefighters get there, if he stops breathing or it gets really slow, I want you to call me back, and we're going to start chest compression CPR. Okay? Just keep an eye on it. Okay. And I want you to look at it one more time before I get off the phone here. He is breathing normally for sure. Is that correct?
I mean, there's blood coming from his mouth.
So I'm just gonna stop it here. Hopefully the call made sense in terms of what happened. This was a real emergency medical service phone call happening in Seattle. And what you can see in this phone call is our software. To the left in this pane, you see the protocol that the human call taker can click through. To the right, you see our machine learning detections throughout that call. It's detecting symptoms detected live in that conversation. And it's all the way down to, for instance, a possible cardiac arrest detected after 40 seconds. The interesting thing about a possible cardiac arrest detected here is that the caller that called in, if you're really aware and listening here, the caller that called in said that the person is unconscious, but breathing. And that made the call taker believe that this was not a cardiac arrest call. And therefore, the call taker is taking much more time than what would normally be the benchmark for detecting a cardiac arrest. And basically, that is happening a lot of the time in these human conversations, that there is some ambiguity because of the stress of this conversation, and because things need to be happening so fast that one of the either the call taker or the caller is doing something wrong. The call taker not listening carefully for what's happening. The call taker is also under a lot of stress in making the right decision in this call. The call taker can definitely feel that something is wrong, and that call taker wants to do the best. And the caller can be basically telling a lie, basically, which the caller don't know is a lie, right? That the person is breathing. And that's because the caller in this instance believed that the person was breathing, but that was in fact just lung cramps happening in the background, which is also denoted agonal breathing. So the AI is listening to all of these features and then it's saying during this phone call that a possible cardiac arrest happened after a 40-second. And a possible cardiac arrest means that that's a cardiac arrest where it can detect with a higher false positive rate. Later on in this demo, it detected a cardiac arrest for sure. And then the call taker needs to take that into account. So basically, we have built the analytics platform as well. That before you saw was the augmentation partner and analytics platform to use all of these machine learning features in order to get smarter on what is there in the phone calls across all of the phone calls, in order to make analysis on the call taker performance, the performance of the protocols, and so on. And then we've also built this triage application to be front-facing towards the patient. so that the patient can basically click through a patient related self triaging functionality in order to triage themselves before they call in. We've also built towards these acute matters. For instance, for the COVID-19 crisis, we use all of this AI data in order to flag cases across the community, as you see here, where we can basically see whether a caller that calls in has a high probability of being a COVID-19 patient. And when all of this cool technology has been disseminated here, this is what reality looked like. This is the a normal everyday view for a call taker that is receiving a phone call and have enormous amount of data inputted to their minds, from mapping data to telephone system data to our application that you can see right in front of this call taker. One of our first and foremost missions here with this technology is that they will only have to look at one interface during a conversation, such that they can have more brain power in focusing directly on the dissemination as compared to all of the maps and so on. What is happening behind the scenes? Now we're trying to dive into where it becomes interesting, right? We take the audio and stream it in through our framework, and first of all we run it through a uncertainty estimation, an acoustic model that is trying to take the acoustics out of the conversation. We apply some language modeling in order to get the semantics out of the conversation, and then we apply natural language processing on that, and then we finally give a recommendation. And the recommendations was what you saw to the right in the pane before. We partnered to begin with the emergency medical services that were the best within research and data in the world, and the reason why we partnered with them was in order to prove the efficacy and the efficiency of the platform, and thereby get a validation point from the best in the world, and for the fact that they could actually see that it worked better than when the human being was by themselves. We started with cardiac arrests, as you might guess and imagine from the demo before, because cardiac arrest is a very serious illness. It's if not then among the most acute illnesses that an emergency medical service can respond to. The accuracy in detecting them from a call taker's perspective is on the high side. This example over here is from Copenhagen emergency medical services, and that's with a 72% sensitivity on recall. So basically, we trained the system on 14,000 hours of emergency calls to begin with, and we detected whether it was cardiac arrest. We took out all of the population data for two sites, two populations, one for Seattle and another one from Copenhagen, and tested how the efficiency of the human was before. We started with the machine learning, and then we saw that the machine learning was detecting quite a lot higher sensitivity than the human being. It was actually able to, with a slightly higher false positive rate, to detect 50, approximately. It was 43 to begin with, but a little bit more now. 43% of the previously undetected cardiac arrest cases. Hence, these are 43% of the previously undetected calls that were calling into a 112 service. The machine learning is able to flag to the call taker and say, this is potentially a cardiac arrest. We're currently increasing the capabilities of this towards stroke, sepsis, and suicide, and we're also taking it into maternity acute phone calls, and also psychiatric interviews. And the psychiatric interviews, we have learned a lot from the emergency medical services, and that's drizzling down the funnel all the way to psychiatric interviews from human to human, when a doctor is trying to find out what illness a patient is suffering from. These are different psychiatric categories that we're currently looking into. If there's anyone that are interested in research within this, then please reach out afterwards. So basically, I'm first of all gonna tell you one thing about this machine learning service, and that's we have worked for a long time on knowing where we are in the conversation. So imagine that we have the audio coming in, and the audio is one stream information, where we get a lot of questions from the call taker, we get some instructions from the call taker, and then we get a lot of questions from the caller, and we get a lot of information from the caller. The call taker, at the same time, as you saw from the demo in the left pane, is having a protocol to the left of where they're working, and the protocol is basically an algorithm that they try to follow to the best of their efforts in order to make sure that they comply towards the fastest trusted triaging path. From a machine learning perspective, there is an interesting task in taking the audio stream and matching that to the protocol. Hence, do we know where we are in the protocol given the audio? That might seem like an easy task, but it's far from easy, because the different questions can be given in various ways. What is written in the protocol is far from always just the question that they need to ask. It can be guideline information, medical information, but there is a link between the question that they ask in the audio and the information that is in the protocol. And as soon as we knew where we were in the protocol, then we can start recommend where to go in the protocol. Hence, this is a mission critical system, and we need to make sure that our recommendation on the next step in the protocol is also a recommendation that is validated medically. So we can only take paths that are validated given the algorithm that they should follow. Hence, we need to know where we are. So basically, we are taking in the audio and we're checking for whether a answer can be mapped to a question that can be mapped to what is denoted on this slide as a knowledge base, hence the protocol. We have a new paper on that specific topic published at the Association for Computational Linguistics 2020, where we basically take the audio modality in and we take the semantic extraction from our automatic speech recognition models, and then we take those two representations and add that into another model, deep neural network, that is trying to find out whether this is a question or whether it's something else. As soon as we know whether it's a question, then we take that out and then we cross relate that to the protocol and try to train that against the protocol. Please go in and read the paper. I think that it's really nicely written. I was only a far down co-author, and I really enjoyed reading about this work from the team, because I think it's really solid work. That was a table on the results. You can go and read the paper afterwards. What I want to highlight here is that just to end the introduction of also the product part, is that as mentioned before, we can be a part of the pre-screening of these conversations. We can be a part of the augmentation part of these conversations and the analytics part. Now, recently, we have basically also created a voice agent for the pre-screening that can basically talk in the phone queue, as mentioned before. I can try to give you an example of how that sounds right now. And basically, this voice agent is using the information from the real phone calls in the augmentation part, hence the phone calls where a human-to-human interacted, and it's using that information to reason on the conversations where it's basically just an automated agent that is having the conversation with the end user. And when that is set, we cannot, with this technology, replace the human in the emergency medical service phone call. We can only be a good replacement when there is no human there to attend to that call.
Hi, Claudia. Adia here. I am following up on your last COVID-19 assessment. How have you been feeling lately?
I've been feeling a lot better since we talked the last time.
Understood. Are you sleeping more than last time we spoke?
Yes, a lot more.
All right. Is there more that come to mind?
No.
Okay. Have you felt physically fatigued during the last week?
No, I have not.
Understood. Is there more that come to mind?
No.
Hi, Claudia.
Oh.
Hi, Claudia.
No, I'm repeating it. I'm sorry about that, but you basically get the gist. This is an agent that can use the questions extracted from the real conversations and then utilize that for having a conversation directly with the patient in hand. As you can hear from this, this is our first beta version of that. We are intending to go live in situations when there's no medical professionals there, to ask the first questions and get that information from the user as quickly as possible. And as you can hear, it's difficult to really make a nice flowing conversation, and that's something that we work heavily on. It's a work in progress, but I thought it was interesting also to provide this this small demo for you to have a listen to. So to the main title of the presentation. I'm sorry for taking so long to actually get to this point. In these kinds of situations, when someone is calling in and having a machine learning system like ours, we need to ensure that we are certain. We need to ensure that we are certain on our predictions. Modern deep learning are not providing that capability, and I might as well just say it now that even though you apply a sigmoid function at the end of your neural network or a softmax function at the end of your neural network, you're not gonna be able to use that as a confidence metric. I'm gonna give you an explanation to why that is. But first of all, to the quote from Richard Feynman. I'm a big fan, and I don't normally use that many quotes, but I really like this, and that is: what I cannot create, I do not understand. And when you go to neural networks and apply these really big models to complex data and try to use them for discriminating, these models cannot create the data again. Hence, they cannot go back, and if you say, give me this class, then give me the input sample for that class, for instance. They cannot do that. Hence, if they cannot create it, they do not understand it. Just to be a little bit dramatic here, and going back to the serious part of this, in my belief, this is very important to be serious about, because we're applying these deep neural networks, these extremely big models, where we don't really have a control of their caveats, and we're applying them to really mission critical environments, such as, for instance, an autonomous vehicle, that is driving around with human beings and can be overly confident in situations where the engineers had no idea that they were overly confident. We can see that as examples with adversarial attacks. Some people can see that as a fun and giggle game that you can play adversarial attacks towards the deep neural network and make them completely failing some of their predictions. However, in real life, failing a prediction can have severe consequences. So let's go back to Pearl and his saying that we are learning associations in data, and we are learning associations in data by discrimination. Hence, we take in some classes and we try to discriminate between these classes, whether it's these round solid circles or whether it's these X's down here. Then we're trying to learn a classifier that can discriminate the two classes. In this example, it's quite easy just to draw a line in between. In this example, when we have images of cats and dogs, then it's also quite simple to tell the model that this is a dog, this is a cat, this is a dog, this is a dog, this is a cat, this is a cat enough times with enough data until the machine learning model has learned to classify that quite accurately. However, what happens to the model when it has been learned on cats and dogs, and we suddenly introduce a fox? How would the model act? Your hope could be that a fox looks more like a dog, so it would probably maybe predict the fox as a 70+% dog. It could also predict it as a 100% cat, and that's the main point here, that we basically don't know. And the reason why we don't know, or the intuition to why we don't know, I would like to show you now. So we have a top half moon and a bottom half moon. That is our data set. I enjoy this data set because it's extremely simple. And these are in fact scatter points that are very densely connected, and so densely connected that they even look like two lines here. So it's difficult to discriminate between the two half moons by a line. And therefore we need something that is nonlinear in order to discriminate between these two half moons. Yeah, I show that here. And basically, if we create a very small neural network, yes, a very small neural network can solve this very simple problem. Fortunately, or if not, then that would be a very, very annoying problem. But if we take a very simple neural network and we define one of the hidden layers, maybe the only hidden layer in this example, as 2 units. Then we can represent the latent representation of the data in those 2 units without having to make PCA. So you get the brutal truth of what's happening inside the neural network. To the left here, you see the classification learning as the neural network is learning. So you see how it learns to classify and discriminate the 2 half moons from one another quite fast during learning. And to the right, you see how the latent representation is skewing and bending the input distribution until the point where it can discriminate the 2 half moons linearly from one another. Hence, that is what's happening. That's why we are applying these nonlinear functions on top of each other. That is because they are able to transform the input space in various ways, and thereby discriminating linearly. So let's say that we have a model that is trained on these 2 half moons, and it has learned them to perfection. That is this example. What then happens when we suddenly introduce some new half moons to the left and the right from the original half moons that we used for training the neural network? What is happening is that the neural network will discriminate them as it will have learned nothing about the structure of the 2 half moons. So it will basically say everything to the left of the half moons that it was trained upon are classified as the top half moon, and everything to the right are classified as the lower half moon. If we were in a human interaction perspective, I would ask you a lot of questions back here to why that is. But basically, what's happening here is that it's basically learning that outside of this region, the highest probability of this being there must be a higher probability of this being blue half moon to the left, because that was where the highest density of data points of the blue moon was placed, and vice versa in the right region. So back to the creation part. I have 7 more minutes, so I'm gonna sprint a little bit here. Instead, I would like to introduce a model where we can ask the model to create the input distribution. If it can create the input distribution, then it also has a certain understanding of how the input distribution was generated. What you saw to the right was basically a generative model that generated the input data distribution. What you can then do is that you can make a density plot and from the model, and thereby ask the model whether a new half moon introduced is outside of the known distribution. Thereby, you cannot go back to the half moons from before and say that this model will be better at classifying all of the moons to the left and to the right. But at least you can ask the model whether it's confident about placing a prediction on those moons. And given the density plot, you would be able to see that the model would say, no, I'm not confident within this region, and thereby I do not want to predict. In our scenario, that is something that we really want to become even better at than we are today, because it's much more important to sit with a medical professional and say, we don't know right now. We are within the regime where we don't know, and you're on your own, instead of trying to predict something that is completely orthogonal to what is the truth. And also, we would like to flag these low confidence data points, since we can then use it to flag it for training later on and learning from those data points, because those are really the important data points to learn from, back to the infant learning to to interact with the environment from the ladder of causation introduced earlier. Given the restrictions towards time, I'm not going to go too much into this, but we've been working quite a lot with variational inference and variational autoencoders, and also been working on how to expand on these variational autoencoders. These are probabilistic models by design. Have a discussion on how probabilistic they are, but at least they give an ability to quantify the certainty of a data point given the data generation process of the model. This is a variational autoencoder. That's how it's defined. It has a generative model where it has a latent distribution set, where it can basically, from that latent distribution set, it can generate the input distribution X. The better it is to generate, the better the model is. It can generate that input distribution X given the parameter setting theta. And then in the variation autoencoder setting, then we also have an inference model where we basically take the input data X and infer that into a variational approximation to the true posterior distribution set. And that is done under the parameter space phi. I'm not going to go too much into the model specifics because we simply don't have the time. But I would love to geek away, as you can probably see here. But basically what we want to use these models for and want to become better at using these models for is learning a distribution over our different settings of these of our medical consultations, such that we have a good understanding of the distribution of a seizure as opposed to the distribution of a stroke, as opposed to a distribution of something unknown, where in this example it could be a cardiac arrest. Thereby we can say if a lot of data points falls into that gray area up here, then we can say, hey, we have a low confidence here. There is probably something new that we didn't know about. I'm going to give you a small example of some of the caveats of these models, and then I'm going to refer to our neuroinformation processing systems publication from 2019, where we developed a certain form of deep latent variable model, which is a form of a similar model as a variation autoencoder on image data. Image data is just easier to work with than audio because it's more visual, also for the publications. But a lot of it works in a similar way. So one of the issues with these latent variable models is that they're not, especially the variation autoencoders, is that they're not that good at generating really complex data distributions. I can talk for hours about that, but basically buy into the fact that they're normally not that good at it. On top of that, general generative models with an explicit likelihood, such as autoregressive models and flow models and variation autoencoders, they are not very good at quantifying whether they're uncertain about an input data point. And that's kind of mind-boggling because they should be, right? If they learn to generate, they should be able to learn or know what they don't know by generating and comparing to that generation. But they're not that good, and I can really recommend that you read the Google DeepMind paper on that topic. It's named "Deep Generative Models Know What They Don't Know." It's excellent, and it's really showing some of the problems with these models. And I enjoy reading these kinds of paper because you learn more from what doesn't work than what really works. So we basically sat down and tried to formulate a model that could actually learn a good confidence of the input data distribution. And one of our problems with these models was that they were simply not deep enough. And this is not deep neural network deep per se. It's deep latent variable models deep, since we believe that if we made just a deeper latent variable model that could learn more covariance between the latent distributions, then we could also have a model that learned the what we denote the global features of the input distribution better. And these global features denoted is, for instance, the higher representation on a manifold somewhere on a lower dimensionality of where a dog should be placed as opposed to a cat, not the not the local features such as the edges of the natural images and so forth. So we sat down and formulated this model that has a bidirectional inference model, and the reason why it has a bidirectional inference model is because it can then learn from the input data distribution in a forward backward mechanism. And when I say forward backward, it's not temporally, it's hierarchically. So, long story short, you can read the papers down here. Basically, when we inputted a data point, we could see the higher up we got in the hierarchy, the more flexibility the model got in order to generate a slightly different picture. So what you see here is an input picture image that we give the model, and then we ask the model to generate it from one of the lower representations. And there you see that the input image is very similar to, or the generated image is very similar to the input image. The higher you get, the more dissimilar it gets, but it still keeps the same style as the input image, similar to the other images you see down here. If you start looking at the different images, for instance, here is a male with longer hair. And as you can see, what the model does here is that when it generates from higher up in the hierarchy, it tries to convert this male into a female. And that shows us that the model is not as confident with this male. And we can also show that in numbers, but this is intuitive from the generations, right? And what it also shows us is that the model then has a certain bias. So when there is a male with longer hair, then it has a bias towards this being converted into a very different part in the latent representation. What we can use that information for is that we can use it to retrain the model on more males with longer hair. You can also see up here that it takes in a person with sunglasses, and then it transforms those sunglasses into regular glasses. There's probably a higher representation of regular glasses in this data set, and then finally it removes the glasses. Finally, you can see that when we walk around in our latent space, we can start from the very center of where there's a center of mass in the distribution. Then we can walk out to the outskirts of the distribution. When I do that and play this for you, then what you see here is that at the very mode of the distribution, they're very similar. But what you could also see that there is something about the skin color. It's certainly overrepresented from a certain ethnicity as opposed to another one, and thereby you could also learn that there should be a higher distribution of another ethnicity. And thereby you know that the confidence when predicting on another ethnicity is lower, and thereby you should be concerned about the model's efficiency when predicting within that. That to make a relation here is, for instance, us. We have a continuous problem with different accents within the language, and knowing exactly what input gives a poorer prediction from our down the line models, and that is something that we use this technology for. That's it. I was 4 minutes over time. I'm sorry, Vince. Hopefully, there's time for some questions.
Absolutely. Can you see me, or do I have... Oh, I think I have that problem with my camera again. I'm very sorry about that. We had it before. I restarted my computer, then it worked, and now again it doesn't. So you have to see me with the dark screen. Lars, thanks a lot for your presentation. It was very interesting. You can hear me, right?
Yeah.
Okay, great. So thanks a lot for your presentation. Yes, there are a few questions, and let's go through the questions on Slido. So the first question, actually, and I just pasted here also in the chat so I can show it on the screen, is how do you handle data privacy in the training process? Lars? Lars, can you hear me?
I think he can't hear us. He might not hear us.
No, he just reconnected. So, Lars, can you hear us now?
Yes, I'm here. It just stalled. Hopefully, it was just at the end.
Yes, I did. Okay, so sorry about that. So thanks a lot for your talk, Lars. Sorry about the technical glitch. So the first question, so there are a few questions. The first question is, how do you handle data privacy in the training process?
Yeah, very good question. So we have some very good partnerships, and with those partnerships, we ensure that for the partnerships where we train the models, we train the models within within their infrastructure. So a lot of the partnerships are cloud-based, and we basically have the ability to tap into the data within their cloud organizations, and thereby we don't have to take the data out. But we are able to then take the machine learning model and then bring that over to a different customer and then predict on their data later on.
Okay, thanks a lot. So the next question is the information from the call also forwarded to later stages? So e.g. the first responders arriving at the scene or the doctor in the ER?
Yeah, so we use that for training all of that data, and we use that in order to point the machine learning models towards a certain towards learning from the data in a better way. But it's not used currently in the live setting. We are going to use some of that information soon, and that's using especially for nurse advice lines that are of a lower acuity, where the medical professional is retrieving the electronic health record data. And there we are going to insert that into the machine learning models as metadata. Basically, we are also having a project right now, and that's for the psychiatric evaluations, where we use video data with the audio data in order to predict on that.
Okay, thank you very much. The third question is, how do you handle different languages? And a follow-up question seems to be, do you see benefit of transfer learning for related languages, English, Danish?
Yeah, really good question. So yes, we do. We do see some crossover. I believe that there are some papers that has claimed a little bit more of crossover than what we see currently. But especially where we see a crossover is from related languages like Danish to Swedish, or UK English, Australian English to UK English, US English, Australian English, US English, and so forth. We do also see something from for instance, Danish to English, where some of the auditive features or the connotation features and so forth, they are helping in better what I denote, and that's really boring, as a better initialization of the neural network than just a random initialization.
Yeah, that's kind of makes sense. And the last question from Slido is, this is probably related, I guess, from it to the part where you talked about the half moons, the prior knowledge. Isn't the problem in the medical domain that we often don't know in analogy what the two half moons are?
I'm not particularly sure what is meant by that question.
Sorry.
Yeah, no worries. So in a human-to-human setting, I would love to ask for elaborating the question, but I can try it out and say that yes, I guess that if what you mean is that there can be a fuzziness on the correctness of an annotation, and by that I mean that the diagnosis given to the patient can be fuzzy in terms of another diagnosis, and it can be really difficult to discriminate between two diagnoses and whether a diagnosis is correct. I imagine that is what is meant by that question. Then yes, that is somewhat of a problem in the medical domain. However, we can train these models such that we don't just train it as a mutually exclusive problem. So we can train it such that different diagnoses that are related, or different outcomes that are related, can be trained towards the model such that we just weigh them according to their relation, and thereby the pure discrimination between the outcomes are not too important.
Okay, thank you very much. So I hope whoever asked this had got the answer that they wanted. I actually have a final question on my own, and that is if I understood it right, so you're kind of saying, and this was the nice picture also where you showed like the steps of the images. This is kind of like usable to kind of quantify bias within a data set without any external data set necessary. So is that correct?
Yes, exactly. So you can basically see where your weaknesses are.
Yeah, because this is very, very important, because as probably many of the viewers and also you're aware, but one of the biggest problems that we have with medical data is bias, and also how to quantify it and how to get an idea where problems are that you might not even know. And with this, you could kind of get an idea, wait a minute, here's something happening that I haven't even thought about. Because the other way is to look at something that is especially like in machine learning fairness, to look at things that where we know that problems are, like gender or race or something like this. But there might be problems that we're not even aware of, and I think this is really something like if that will be very, very, very important in the future to make data sets better and to develop better tools.
Yeah, exactly. You're definitely right. So I couldn't agree more. And there's a lot of research to do. So we're still researching in this. We actually started a PhD program with the university right now, where we research further in the certainty and quantifying uncertainty of a data point. And we are also researching quite heavily within basically making adversarial attacks on our own machine learning framework in order to test whether there are some weaknesses on language origins or different socioeconomic groups and so on. So yeah, if there are anyone in the crowd listening that are interested in those topics, we're more than happy in order to set up a collaboration.
Sounds like a really, really cool research project. Zsófia, do you have a question to add or anything to add?
No, not at the moment.
Okay, Lars, do you want to say some final words?
I'm good.
Okay.
And thank you so much for the presentation or the invitation, and thank you for listening to me.
Presentation. And thank you so much that you gave us this talk. It was really, really highly interesting. And thanks a lot to everyone tuning in. Sorry about this glitch in the end with my camera. We'll try to figure it out until next time. And otherwise, have a nice evening. And thanks for joining. And thanks again, Lars. Thanks, Zsófia. And see you next time. Thank you. Bye-bye.
Thank you.